Question 43. Sketch the graph of the function f of x equals x squared over x squared minus x. So this is a rational function. The first thing that I'm going to do with this graph is I could see that a common factor can be removed. So if we notice, the bottom can be simplified as factored as x outside of x minus 1, and then the exponent will cancel out the x on the bottom, so we're left with x outside of x minus 1, with the exception if we canceled the 0 on the bottom, so x cannot equal 0. So this is the graph that we want to do. The other thing, I guess, while we're on the topic, is the other kind of restriction. We know x cannot equal 0. When we look at this factor, we see that. When we look at the other factor, if we solve the factor of x minus 1, we see right here that x cannot equal 1. So let's investigate the behavior. First, we're going to investigate the behavior of f of 0. And obviously, when we put f of 0 into our original function, we get the behavior of 0 over 0, which is an indeterminate form. So it's better to put f of 0 into our other function right here and see what we get. So we know it is a restriction and it's not defined at that point, but we're going to investigate whether it's a whole or an asymptote. So this becomes 0, and then on the bottom is 0 minus 1, which is negative 1, so this becomes 0. So because f of 0 is giving us 0 in our simplified function, we know that there is a whole, and the coordinates of that whole are 0, 0. So how do we indicate a whole at 0, 0? 0, 0 is the origin. So we will draw a little circle right at the origin. The other asymptote, or sorry, maybe I'm foreshadowing. The other value, the other restriction, if we look at the denominator here, x cannot equal 1. If we try f of 1, we will get 1 squared, which is 1. And then on the bottom, we would get 0. And that is asymptotic behavior. So there is a vertical asymptote at x equals 1. So I'm going to draw in that vertical asymptote as well. All right, so that's first thing we looked at, the restrictions. The second thing I want to look at is the end behavior of this graph. And by end behavior, I mean as x gets really, really big, and in calculus we'll learn about the limit as it approaches infinity. But as x gets really, really big, what happens to y? And what happens to the graph? So in order to look at end behavior, we only need to consider the largest exponents in our graph. And the largest exponents in our graph, f of x will take on, what really matters is the x squared on the top, and on the bottom, the x squared. So x squared divided by x squared equals 1. So that is pretty much our end behavior. In another way, we could say as x goes to infinity, y goes to 1. So that is a horizontal asymptote. Horizontal asymptote at y equals 1. So I'm going to write in that horizontal asymptote there. Try my best at least to write in that horizontal asymptote. So we got two important bits done, and we still don't have a graph. So it's a choice here. You could do some kind of transformation and see if there's a parent function that this is a transformation of. My preference is to do something a little more basic, and that is to do table of values. So in order to do a table of values, I would prefer we use the simplified function x over x minus 1 because we know what's happening at the whole. So in order to do table of values, there's a couple things that we're going to want to put in our table of values. Mainly x and y, and some values. So I'm going to probably go back to minus 3. So minus 3, minus 1. Oops. Maybe I'll try minus 2, then minus 1. And then I'll try 0, but 0 is our whole. So I'm going to skip over that part for now because I know 0 is my whole. And I'm going to skip over 1 because I know 1. Now, what I want to do is probably pick some values in between, though, 0 and 1. So I'm just going to pick a 0.5. I'm going to try 0.5. And I'm going to try a 1.5, because we don't need to know 1. That's the asymptote. And then I'll continue on in my pattern that I was doing before. I'll probably go 2. Whoops. I'll go 2 and 3. So I want to do those values, and just so I have it in sight down here, remember my function is f of x equals x over x minus 1, reminding ourselves that it's not true when x equals 0 because that's our whole. So let's substitute in the minus 3. If we substitute in the minus 3, we get minus 3 on the top. I'm going to do this in my head. Minus 3 minus 1 is minus 4. So two negatives make a positive 0.75, a positive 3/4. Remember, this is non-calculator. So my minus 2 minus 1 is minus 3. And then it's a 0.66. And then we got our minus 1. That's a minus 1 divided by minus 1, which is minus 2, which is 0.5. So that's good so far. I'm going to keep going, and then we'll make some sense out of this after. So I got a half, and I'm dividing by 1 minus a half. So that's minus a half. And that is negative 1. I have a 1.5. I'm dividing by 1.5 minus 1 is 0.5. So two positives is going to stay positive. Dividing by half is the same as multiplying by 2. So if we double 1.5, we get 3. And, some people may say this is an overkill. We know the general behavior, but I'm going to keep plugging away here. It doesn't take that long to do. 2 divided by 2 minus 1 is 1, which is 2. And then 3, I got a 3 divided by 3 minus 1, which is 2, which is 1.5. So hopefully we can make sense out of some of these points. So I'm going to warn you, my pen is not working that well today, but I'm going to try to put it in as accurately as I can. I'm going to place these points. I'll just go with black points today. So we're going to go negative 3. So the label's already, the axis does have a 1 on it, and the x and y. So we don't need to add additional labels if we don't want to. If it didn't have the 1 and the 1, we would add them, but negative 1, negative 2, negative 3, 0.75. So 3/4 of the way up. Try to judge this appropriately. Not good. Okay, way too high. Sorry about that. Okay, I'm going to keep going. 2/3 of the way up. Not working out. Half the way up. There, that was better. And a half, we're at negative 1. Which makes sense because we're going down, obeying the curve of the asymptote. 1.5, we're all the way up to 3. So I gotta change my window here. 1, 2, 3. So 1.5, we're all the way up to 3. All right, we'll try that. So 1.5, we're at 3. And we'll put that in. Okay, and then I should try to memorize these. 2, we're at 2, and 3, we're at 1.5. So 2, 2. 2, we're at 2. and then 3, we're at 1.5. So there's one thing I see is the asymptotic behavior coming into play. You could see ideally the curve is obeying the vertical asymptote. Sorry, it's obeying the horizontal asymptote on the ends. It doesn't have to obey the horizontal asymptote in the middle. But as x gets really, really small, it's obeying it and going to 1. Then it's crossing through over the hole. Then it's going down, following the asymptotic behavior. Similarly, on the right side of the asymptote, as x gets big, the graph is going down and it's following the asymptotic behavior. So I'm going to attempt to draw my curves in here. Hopefully it looks good and it'll all make sense. So this is a little difficult here. No, way too high. But you know what I mean. A lot easier when you're using a pencil. Don't ever go above the asymptote. And we'll try this again. Okay. So that's my attempt. The only thing I change is probably obey the asymptote on the end there. But it's not so bad. I hope this helped you out. Okay. Again, we looked at 3 main things when we did this graph. We looked at our restrictions, investigating whether they were holes or asymptotes. We looked at our end behavior, and that's really looking at what happens for the highest powers of x in our degrees of our numerator and denominator. And then to complete the picture, we did a table of values and we graphed it.